See if we can max out the performance on my PC. All right, so today what I was going to start with is we were going to run through another one of the voltmeter designs. It's kind of good practice just for series circuits, unless anybody has any other questions to start with about any of the other math problems, the fractions or just basic series circuits or anything like that. Okay. If you do have questions, like I said, I'll go through and answer them. Today's kind of that. It's just a review day. I don't have anything more to lecture about. So we'll just continue to review, and if you have questions, answer them. So grab a marker. So we'll start off by drawing our resistors and our circuit. Okay. So with our basic circuit, and I will start writing the ranges up. So the first things that we have, our I meter is 2 milliamps. And we have 60 ohms for our resistance of said meter. Range 1. Oh, let's have some fun with this. I'm going to go 25 volts. Range 2, 250 volts. Range 3, 2.5 kilovolts. And 25 kilovolts. It is a lot. Like I said, some tools you have that you'll work with those. Like what Zach was saying, when he wants to work with Rocky Mountain Power, he's going to be dealing with these high voltages coming in. Not necessarily DC, but you can still build these. Okay. Give everybody kind of a chance to write that down. What would your guys' feelings? Do you guys want to work through it a little bit yourself, and then we'll start calling people to walk through it? Okay. So let's go ahead and do that. I will leave that up there. Go ahead and take a few minutes and get it written down and start working through it. At least starting on getting through range 1. And we'll go from there. Okay, I'll give you guys about another minute and then we'll start answering this. Let's see. Let's find some good ways. All right. So many ads. Alrighty. So let's go ahead and get started. It is aggressive. That's what makes it fun. You don't mess with the wheel. The wheel will get you every single time. Okay, so when we're solving for these guys, where is the first step that we want to do in solving these? Find the voltage of the meter. Okay, that is the easiest step to start with. Okay, and what's the formula for voltage? I times R. So I meter times R meter. (120 millivolts). Okay. So we'll go through this and we'll solve it this direction, and then I'll show another way that we can go through it as well, just depending on how you want to look at these guys. So 120 millivolts is all that we have being dropped across the meter. Okay. So the next part, we need to figure out where do we go from here. Jameson. Okay, where do we go from here? Okay, and how do we do that?
So we're going to subtract 25 volts from our 125 millivolts. That should give us the total voltage. Then we need to divide that by ohms, or not ohms, current.
To get the ohms.
Get the ohms, and I'll get the resistance for that resistance.
Okay, So basically what he's saying is we need to find, so the first step is we find the voltage of our meter. Second step, we need to find the voltage drop that's going to be across R2. Now remember, when we're looking at this guy, we're only in range 1. So our switch is in the range 1 position, which means R2, R3, and R4 we don't even care about because they're all connected to an open. They're just hanging out. They're not doing anything. Worst case scenario, they're going to act as an antenna. What'd you say? Yep, just mad chilling. Okay, so how we find the voltage across R2 is it's going to be the voltage of the range that we're at minus any previous voltage drops that we have already found. So with this, we know the voltage drop here is 120 millivolts. We know we have a max of 25 volts coming into this spot. So the voltage for R2 is going to be equal to 25 volts minus 0.12 volts. Because that's all that's being dropped here. So the voltage drop across R2 is, what would you say, Jameson? What was your answer? 12? That's your resistance.
Oh, my bad. Yeah, no. Volts, it should be. That should be 24.88 volts.
There we go.
I got it.
Yes.
When you say like voltages R2, do you mean R1?
Yeah, that's what I meant. Yes, the voltage of R1. My apologies. Okay, so then then what Jameson was saying, so now we have the voltage, we have the current, because in a series circuit, the current's going to be the same. So R1 is going to be equal to the voltage drop across R1 divided by the current going through it, which in this case is I meter. Gives us 24.88 volts divided by 2 milliamps. And that gives us the 12.44 kiloohms. So we're just working backwards, finding what we can solve for, what makes it easy to do, and then stepping backwards. Any questions with this first step, or first couple of steps, I guess? R1 again? Yes. Okay, so how far back do I need to go? 0.12. Okay, so in this instance, we are looking for the voltage drop that we're going to have across R1. We have 25 volts coming into the system, so that's our input. We're dropping 0.12 volts over here, so the rest of the 25 volts has to be dropped across R1. And so that's where we get the 25 minus the 0.12 or the 120 millivolts, which leaves us a total of 24.88 volts. We good there? Okay. Then, since we have that voltage drop, we know we have this current because these two are in series. So we have 2 milliamps flowing through R1. We then can use Ohm's law to give us the answer for what we need. So 24.88 volts divided by 2 milliamps is 12.44 kiloohms. Yes?
So earlier today you were showing me a different method.
Yeah, we'll talk about that here in just a second.
So then you need to use these interchangeably depending on it, or do they just go through?
You just do one way or the other. Make sense? We good? Okay. So now we need to go and we need to find the voltages and resistance for the next set. This is as far as we can go in range 1. So the next step, we're going to break the connection and we're going to turn the switch to range 2. Seth. now, so this was range 1. Now we are in range 2. What do we need? Where do we need to go from here?
Okay, 250 volts, value of range 2, minus the value of R1, you already found it. And you're going to put all of that over the total current.
Yep. And don't forget about V meter.
Yes.
Okay. That's going to give us the voltage drop across R2.
Isn't the voltage of range 1 include voltage of meter?
Do what?
Doesn't the voltage in range 1 include the voltage of the...
Yes. Did you say range 1 or resistor 1?
I said range 1.
You said range 1? Okay. Yes. Yes, they do. But in this case, I just want to make sure to point out we're still including everything, even though we're not necessarily calling that's what it is. So VR1 and V meter is V1. So when we move forward, so when we move to the next one, V2 encompasses everything. We already have that solved, okay, because we're building everything to accommodate this fact. Okay, so we end up with, yep, 225 volts.
And all of that, the 225 over the 2 milliamps.
So voltage of R2 divided by the current through R2.
Which should give you 112.5 kilo ohms.
So basically all we're doing is the same steps. Okay, we're looking at how much total voltage we have. We're looking at how much voltage do we have for everything previous, and since we've already solved for it, when we adjust our switch, we're not changing the resistors themselves. All we're doing is physically turning this switch. So think of your guys' DMMs. When you go to a different range, this is all you're doing. Everything that was already in the circuit still there, you're just adjusting it to a different point in your circuit. So then we end up with, like Seth said, 112.5 kilo ohms. So we're going to use a little bit of deductive reasoning in this. And again, that's why I say, and you guys are going to get sick of me saying this, what do I have? What do I need? And what's a logical path to get me there? That's what we're trying to get you guys to think of, is where is the path to get me to the answer I want? And in this case, we want the resistance. What tools do I have to get me there? Yes?
So, I don't think I've ever seen 112 kilo ohms exactly.
Mm-hmm.
You're just going to like put resistors together in order to get
Sometimes yes.
112? Okay.
Yep. So if you're designing this, obviously you're going to want to try and choose resistors that you can find that are going to give you standard values. So, and let me show you this while we're thinking about it. Oops, that's the wrong one. Okay, that's not the one I wanted. Okay. So here, this is kind of like I said, kind of a little complicated chart unless you see what's going on. So these are all the standard resistor values that exist, that get manufactured on a day-to-day basis. You can get custom ones, but again, those are going to cost you more. So this one has a 1% of a standard value. Basically, this is your deviation. Do I go plus or minus 1%? This is plus or minus 2%. These two charts are the ones that we have in lab. Plus and minus 5% and plus and minus 10%. Those are the most common ones you guys are going to see in lab. That's the gold and the silver bands at the end. So looking at these, so these are all the standard values, but then we have pretty much any combination that you can think of with different like multiplier values. Okay, so we have a 10 ohm, we have a 12 ohm, we have a 15 ohm, we have a 100, we have 150, we have a 1K, we have a 1.5K. So going all the way up there, we needed 112,000. So the closest we could get is we could have a, so we'd have 120K, we'd have 110K. So then at that point, yeah, then we'd have to add in some other values to find out and kind of mix and match these together to get us up to that value. Also, what we could do is if we have a potentiometer, you can use a potentiometer that are several meg and adjust it into right where we need it to be as well. So there's multiple options of the ways to get here. These are just the standard values. I think I have a printout of these sitting on my desk. So these are all the ones that we carry normally day to day, is these standard values. So like you said, 112, not a standard value, but you could piece it together. You could get 100K and you could get a 12K. Now you put those together in series, now you have 112K.
So basically, if you come out to only having like 110K total, can you just add a potentiometer and set the AB leads to 2K and leave the C disconnected?
Yep. Yeah, you can use potentiometer and a resistor. You can use multiple resistors, whatever you need to be. A lot of times you're going to have these resistors, so you'll kind of get close to what you need. If you have to do it in 3 or 4 resistors, there's probably an easier way to do it. Not necessarily designing, but I would probably find multiple values, higher values to use instead of 3 smaller ones. See if you can use one larger one. So like here, you could use 2 1Ks, or you could just use 1 2K. So try and keep the number of resistors down. Obviously, there's going to be times where you can't, but just try and keep your number of resistors down to about 3 or 4 for one value. Won't be all the time, but there will be times where that'll come up. That answer your question?
Yeah.
Okay.
I guess continuing on with that, sorry, but why not just use potentiometers for everything? Is that just a cost thing?
Cost, usually. Like I said, not everything in the world comes down to cost. Sometimes it just comes up to what you can get. Sometimes you can't get, you don't have time to order in 10K resistors or 100K resistors, but you have a whole bunch of 100K resistors or potentiometers versus the resistors. Sometimes it's just a matter of what you have on hand. My last job, we had very few potentiometers and we had racks and racks of resistors. So we had lots of the resistors we could go to. Okay. So now that we have 112.5 kilo ohms for R2. For R1, we've got a 12.44 kilo ohms. So now, do you have a question?
Yeah, it's just, I did R2, but it was the different method. What I got was 65 ohms, so I'm not sure.
So probably, for sure you dropped a prefix. I'm not sure exactly, but for sure you dropped it because it should be getting into the kilo ohms right now. Because you got to remember, we've got 250 volts. We're trying to only have 2 milliamps. So right there, we should have something in the order of magnitudes as far as we should have kilo ohms versus regular ohms. So like I said, I'll go through the other way here in a second. We'll show you how you can do that. Okay. So we're going to go through range 3. So range 3 is set for 2.5 kilovolts. Morgan, you're up. What do we need to do first? 0.125. Meg ohm. Okay, so the exact same steps that we're going through. We have our maximum range for this, or maximum voltage for this range. We're going to subtract off all the voltage drops that we already have for the rest of the circuit. And that leaves us with a total of 2.25 kilovolts that we have to now assign to this resistor. We assign it, we divide it by the current. So R3 is equal to the voltage of R3 divided by the current. And here we have the voltage of 3 minus the voltage of 2 is equal to the voltage across that third resistor. Yes?
So is there any limit to the number of ranges you can have in this?
Nope.
So if you put your ranges closer together, is it going to be more accurate, or?
They'll be a little bit more accurate. So part of the problem is this is going from, oops, too far. This is saying I want to be able to measure up to 25. So this is going from 0 to 25 volts that I want to measure. So you kind of think of your accuracy in there. This next range, I'm going from 25.1 to 250 volts. So now it comes down to your accuracy of the meter, like you were saying. How much am I going to be able to see that needle swing versus 25 to 27 volts? So your scale is getting amped up more and more. So yes, your accuracy is going to start going down the higher your range jumps are. Even in this case, I'm increasing by a factor of 10 every single time. So my resolution, the amount that I'm actually going to be able to see that needle move, is going to get, it's going to take more voltage to be able to swing it.
So is basically just assuming that at 12 kilovolts, you're not going to like 10 or 20 volts isn't going to make that much of a difference?
Yeah. Basically, you're down to the point where, if you're at 1100 volts, 5 to 10 volts isn't going to matter. And in the systems that large, that much voltage isn't going to matter. Because then again, you're still dropping into your realm of 5%. It's going to fluctuate that much just on its own. Yes?
How would the resolution change if you had like a digital display instead of analog?
So the digital display gets into basically how big of a chip you can handle, or how many digits your chip can handle at a time. One of the things you'll learn about in second and in third and farther semesters is you're limited to basically 256 divisions or 255 divisions. So whatever your range is, you figure you split that up, and that's how much voltage it has to increase before it's going to increase your binary digit one value. So again, that gets into your resolution. This one I would definitely want to cut down on the how big the range is, just to give me a better resolution with that. And same with this guy, is you're going to measure this. Your starting value is going to be your base, and then your max value is here. So then that again affects your resolution. So each range you go into, it's going to still have the same number of divisions. It's just how big of the steps are those divisions going to be, if that makes sense. Okay. Any questions with range 3? Does it make sense, at least how we're getting there, step by step? Kind of? Okay. Let's do range 4. Spencer. Sorry, it wasn't fast enough. What was your answer? Okay. So like I said, once you get through the first initial step, these guys become very, very repetitive. All we're doing is looking at my current range, subtracting off all the voltage I have before, and really it's the same set of steps. Even at the very beginning, my range is 25 volts. All the voltage I have previously is dropped across my meter. What's left is going to be dropped across that resistor. And then as you move forward, you just find the difference in the voltages, because that's what's going to have to be dropped against the new resistor. You divide it by the current going through it, which in this case is the meter current, gives us 2 milliamps divided into 22.5 kilovolts. We're left with 11.25 meg. I don't know if we actually have resistors that go up that high. Plus, we have no way for you guys really to test those. We're not going to turn you loose with, 25,000 volts. Sorry, not going to happen. Maybe when you get into 5th or 6th semester, if you wanted to do something like that, you would probably have to supply the taser to do it. Because in all honesty, that's the only way you're going to be generating that much voltage. That's actually, I'm kind of surprised that hasn't happened yet. They built some robot with a taser running around. We have probably 30 robots that they've built that are running around armed with Nerf guns. So really, a taser is not that far out from the realm of what they can and won't do. Yeah, it's already shooting darts. Why not add, prods to a taser with that?
Have you guys ever done like robot tournaments or something?
We have. They have. There's been, like I said, there was one year that everybody wanted to do a Nerf robot, and they said the whole time in lab, the whole floor was just covered with Nerf guns. Because you'd be sitting there trying to get your turret system to mount, and it would misfire. And if they had the thing fully, they learned really quick not to fully load the suckers. Because if you got a glitch in your code that didn't jump out, it would just sit there and go, pop, 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 and just rotate everything through, and then now you're stuck reloading everything again. Yes. Yes. Okay. So these are our final values. Now, there is one other way to go through this to solve for, yes, Simon? Divided by the current of your meter. In this case, it happens to be 2 milliamps. Yes?
Using Ohm's law, like, because you have the voltage, you use the current, and you use Ohm's law to solve for the resistance.
Yep, that's all it's boiling down to is we're using Ohm's law. Okay, so the other way, oops, that went all the way to the top. Oh my gosh. Easy. Okay, so the other way that we can solve this, so this is going through and solving based on the voltages. There's another way that we can go through and solve these guys. Sometimes it makes more sense if to other people looking at it a different way. So when we come through here, let's look back at range 1. Okay, we are looking at the voltage is equal to 25 volts. Okay, when we come back and look, again, it's going to be based on this current measurement. So we know we don't ever want to go over 2 milliamps. So how much resistance do I have to have in this circuit with 25 volts to give me 2 milliamps? So voltage total divided by current. So we have 25 volts divided by 2 milliamps. When we do that, that gives us how much? 12,500. Okay. So we have a total resistance in this branch that has to equal 12.5 kilo ohms. How much resistance do we already have? 60. So if we have 60 ohms there, how much is left? 12.44. So like I said, so you can go through these multiple ways. This way we go through the resistance and look what we have. So we know that we need this much resistance. This is going to be the resistance we have total in position 1. Okay? Same thing. We're going to move on to position 2. The voltage we have is 250 volts. Again, I want to maintain this circuit to only have 2 milliamps max. Because if we go over, what's going to happen? Our meter's going to explode. If it's too low, the meter's going to decrease and show us a relative position. So even if we were putting, let's say, range 2, we were only putting 100 volts through it, where would the meter be sitting? Not quite at the bottom. If we have 250 max and we're putting 100 through it, about, a little less than half, about a little more than a third. So our needle would be sitting, probably like right about there for 100 volts at that range. 200, so 100 volts is here. 250 volts is here. Okay, if we had 200 volts, the needle would be right here. So the needle is still going to adjust and tell us how much of its full movement is basically is it showing. And that's what we're setting this up for, is full movement, full current. Anything less will make the needle not drop or won't go up as high. But if we go over that amount, that's when we cause damage to the meter itself. So in this case, range 2, we have 250 volts. We need to maintain that 2 milliamp maximum going through this guy. So we take how much resistance total we need for range 2, 250 volts, divided by 2 milliamps. 125 milliohms. Kiloohms. 10 to the third is kilo. 10 to the minus third is milli. Okay, so we have 125,000 ohms total that we need. How much do we have sitting in these two guys already? 12.5K. We already solved for that. Okay, so if we have the 12.5K there, how much do we have left? And same for the third and the fourth as well. What's our total voltage? What's the total current? That's going to give us the total resistance needed for that circuit. And then we subtract out all the resistance that we already have in the circuit.
So I'm still not quite getting that. So it's 125 kiloohms minus 60 ohms, right?
So this is already taken into account.
Okay.
We took it into account here.
Okay.
So we need a total of 12.5. So R1 is there.
Okay. So then where did we get 112.5 from?
So here we need a total of 125 kiloohms at stage 2. Okay? We already have 12.5, so we subtract the 125 and the 12.5, and we're left with that amount.
Oh, okay.
And then the same thing for 3. When we're in range 3, that's 2.5 kilovolts. We need the R total for 3 to be equal to 2.5 kilovolts divided by 2 milliamps, which then that gives us like 1.25 meg, I believe.
Yeah, 1.4 R4?
For 3, yeah, for R3. Yeah, anyway, so let's see. 2,500 divided by 2 milliamps. Yeah, 1.25 meg. That's just the total resistance we need. Yeah, then you subtract how much we had from the previous stage. That's going to give us those values. So there's two ways to go through this. We can go through and look at what are all my voltages doing across each of these resistors as we go from stage to stage, or we can go out and look at how much total resistance do I have to have at each stage to maintain that 2 milliamp max. Because if this was ever to go lower, so let's say here at R2 we didn't put 102 k ohms in there. Let's say we only put in 110. What's our current going to do? It's going to climb. We have less resistance, higher current, which means when we pump 250 volts into this thing, that needle's going to go over and then it's going to start bending. And we can physically damage it by running too much current through that meter. That's why overloads, that kind of stuff is worse and it's harder on systems, because a lot of times you have some sort of a mechanical setup somewhere that's going to be, physically bent because it's being pulled on too hard. Plus, you're going to have lots of heat.
So on the DMM, if you put it through a setting and then put too much in, is it just gonna blow the fuse like someone's done a couple times?
It can.
Okay.
But the big thing too with the DMMs is they have protection circuits in them. So they have big heat sinks. They have SCRs, which is solid control relays, that when they get too much current, they shut down and basically shunt all of the voltage through themselves. But they have enough mass that they can withstand the heat. So your meters have those built into them. That's really what the other part of the electronics is. So the electronics is setting up your displays and powering those, but it also does have some control circuits in there to protect itself. It is easy to blow fuses, because like I said, if you measure them in the wrong way, you get a spike in current, you get a spike in voltage somewhere, and it's going to start taking stuff out. The whole idea of the fuse is for the fuse to blow, so you're not blowing resistors, you're not blowing components inside the meter. It makes it easier to replace. Yes. Yep. The 50-cent fuse is easier to replace than the $150 processor.
So how much money do you think Zach's gonna owe you by the end of this semester?
I don't know. We'll see. Honestly, once we get into power supplies, you guys are gonna start blowing parts left and right. We usually have a competition to see who blows the most parts.
Wait, is it for the most?
Well, the most usually brings donuts.
Oh.
It's not a good thing. When I went through third semester, on one of the walls, the instructor went through and listed everybody's name, and every time you blew a part, you had to go mark on your board that you blew a part.
That sounds fun.
And we had one guy, he shorted out his power supply, the power coming in from the plug, the 120 AC. He shorted it out with his oscilloscope probe ground. So he blew a big old hole in the probe of the ground. He tripped the breaker in the wall. Not even the bench one. He tripped the circuit breaker in the wall. We're like, okay, so the teacher came out because he heard the pop, and he was like, okay, who just did what? Because we lost all power to every single one of those benches. It was hilarious. And he's like, well, I've yet to have anybody pop the breaker. You were the first one. Guy had been teaching for 10, 15 years. So he was like, well, I'll give you a break. I'll only make you put 10 parts down. He still didn't lose.
Wow.
There was another guy that blew way more parts than that. Because part of the problem is it wasn't just fuses you start to pop. You start burning up your resistors when you don't think of power. So in these, I just ran through the power calculations just kind of for kicks and giggles. For reference. So the first resistor we designed to handle 24 volts. At 2 milliamps, that's going to give it 49 milliwatts. Nothing. You'll barely even feel that thing getting warm. Resistor 2 is handling 225 volts, and it's only going to get up to 450 milliwatts. You'll start to feel that. It's start to get warm.
But that's when you don't even have to go to, because it is at 250 milliwatts that?
250 milliwatts, half watt, and then 1 watt.
So you have to use a half watt on.
At least a half watt, if not bigger. Where it's that close, I would probably bump it up one more size.
3/4 watt?
Yeah. They don't do a 3/4, it goes to a 1.
Okay.
The next one, R3, is handling 2.25 kilovolts, which is a lot. It has 4.5 watts of power going through it. That sucker's going to get hot. Okay, your soldering irons, If you got them, well, the ones from the kit, those are 25 watts of heat.
So, you need like a 5 watt?
Uh-huh.
Is that a thing?
Yep, we do have 5 watts.
Fat?
They are super fat. They're big old blocks. They're huge. That's not the biggest one. So R4 is handling 22,000 volts at 2 milliamps. Its current is 45 watts. You're talking about a soldering iron. Okay, that sucker is going to get hot. That's the one that you have a resistor on there with a great big metal fins over the top of it to allow the airflow to help dissipate the heat so it doesn't destroy itself.
So at this point, our voltage meter is out EAP.
Yes. Yes, just because of that one resistor.
Nice.
And that resistor is probably, that big. It's not huge, but compared to a little quarter one, it is.
Yeah, I can finally see the colors.
Yes.
No kidding. The quarter ones, you're like, is that, what?
Okay. Do we have any more questions about this power supply? Or not this power supply, the voltmeter? No. This is just a voltmeter. Yes. Like I said, when we get into power supplies, you could build one of these to help regulate what your power supply is. So if you wanted to build a dial for your power supply, you could build a voltmeter that measures your output, and then it's going to track with how much voltage you're putting through this thing. Little bells and whistles. Huh? Yes, we still have to do R4. Okay? So, range 4, we had 25 kilovolts. So the resistance total for 4, hate it when it does that, is going to be equal to 25,000 volts divided by 2 milliamps. It's going to require 12.5 megavohms of resistance. And we had previously the 1.25 meg. So R4 is the 12.5 meg minus the 1.25 meg, which then gives us the 11.25 that we calculated going the other direction. So like I said, either way we can go, we're still using the same principles. How much total voltage, how much total resistance do I have, and then working backwards from there. Just using Ohm's law to calculate it, and some simple addition and subtraction.
What would be the selectivity of it?
Selectivity? You guys tell me.
I got 500 ohms per volt.
500 ohms per volt. Okay? So the way we find selectivity is basically, remember, this is how well our meter is. So every volt that we go is going to have so many ohms of resistance in association with it. Like when we put it across, we want that number as high as we can. So what we want to look at is we can look at any of the ranges. They're going to be the same value, no matter what our range is. So we come here and look, let's look at range 2. Okay? Selectivity. Yep. So our selectivity, remember, is measured in ohms per volt. So in this, we have to look at range 2. So how much voltage are we looking at? 250 volts. So we know that one's going to be on the bottom. And then we're looking at the total resistance of range 2. So we have, 125K, which we know because we calculated that direction. We know the total resistance without having to go back through and add everything up.
Wait, is it that, or is it the 100?
You tell me, what's the total resistance of that range? So we're here at range 2. What resistors are we going to go through? R2, R1, and the meter. So we have 125 kilo ohms. We take 125 kilo ohms, divide it by 250 volts, and we get 500 ohms per volt.
So if we were only allowing like 2 picoamps through, our selectivity would go way up, right?
Yep, because we need a lot more,
Values would also have to go
way up.
get a lot hotter.
They would not get hotter. Just because you have high resistance does not mean high power.
Oh,
It's
that's
the
like
current.
Current is super low, so we're gonna have lower power.
Yes.
Okay.
Could you run selectivity remind me one more time?
Okay. So selectivity is in terms of ohms per volt. So we got to look at our total ohms and total volts for range 2. So range 2, the voltage is 250 volts. That's the max voltage we can have through it. Okay? The resistance is going to be everything that is in that loop.
So I guess if I'm the selectivity for each frequency.
You don't have to. It should be the same for no matter what range we did.
Oh, okay.
Okay? So then in this case then our total resistance was R2 plus R1 plus the meter. And we know from over here when we solved it, the total resistance needed is 125 kilo ohms. Okay, even if we wanted to look at range 4, we have 25,000 volts. The total resistance we have in the circuit is 12.5 meg. We run that through our calculator. And we get 500. So no matter what range we're on, this voltmeter is set up to be 500 ohms per volt. And like I said, that's just how good it is, how much resistance it's going to add going in parallel. You want this value to be high because it's going to affect your circuit less. And like you said, if we had a meter on here that drew picoamps instead of milliamps, that's even better.
Yeah, if it was picoamps, like 500 volts.
Yeah.
No, wait, no,
Nanowatts? Yeah, your power becomes next to none. And that's how they get away with some of these meters that you guys have in there, because they're drawing such little current, it's not going to affect anything that you do. Okay, let's go ahead and go to break.